Welcome. In this video, we're going to talk through the 2013 Equilibrium FRQ, which is related to the Ksp. And I'll assume that you have read through this setup right here, and let's just get started with the first question, which is to write the chemical equation for dissolving magnesium fluoride in water. So I'm starting out with a solid. It's an ionic compound, so when it dissolves, it's going to split apart into ions. So that's my answer to I. All right, calculate the number of moles of MgF2 that dissolved. So if I look through my setup here, first thing I notice is that they tell me that it's a saturated solution, and you made the saturated solution by adding a certain amount of solid to a certain volume. And keep in mind that when you have a saturated solution, we are at equilibrium, and one of the reasons why I know it's saturated is because there's going to be some solid still remaining at the bottom of the container, okay? And some of it will have dissolved into ions. And there you go. So the key thing though is that if it's a saturated solution, there's going to be some solid remaining. So when I try and calculate how much MgF2 dissolved, I can't assume that all 0.5 grams dissolved. Some of that solid is going to remain undissolved in the bottom of the container. So what else do I know? Well, I know that once my solution reaches the saturation point, we measure the fluoride ion concentration and can figure out what it is. So the fluoride ion concentration is 2.4 times 10 to the negative third. From that, and using this chemical equation right here, I should be able to figure out how much magnesium fluoride dissolved. So I know that my concentration of fluoride ions is 2.4 times 10 to the negative third. I know that if I take molarity times the volume in liters, I will end up with moles. And that is because, remember, molarity is a ratio of moles per liter. So I will end up with my moles, which will be 2.4 times 10 to the negative 4 moles of fluoride were created when my magnesium fluoride dissolved. And then I can look up at this equation, use my mole ratio. I can see that for every 1 magnesium fluoride that dissolves, I make 2 moles of fluoride ions. So the amount of magnesium fluoride dissolved is actually 1/2 that of the amount of fluoride ions I am measuring. So 1.24 times 10 to the negative fourth, that's how many moles of magnesium fluoride must have dissolved based on this observed concentration of fluoride ions in my saturated solution. So that's the answer to number 2. Going on to 3, or I guess we should call it triple I, we want to use this information to find the value of Ksp. So we've got our equilibrium reaction, which I think I'm going to write out again. And I'm going to set up an ice chart. When I set up an ice chart, remember we leave solids and liquids out of it because when I write my K expression, I leave solids and liquids out of my K expression. And the reason why is because the concentration of a solid and a liquid does not change throughout the course of a reaction, so they don't affect our equilibrium. We're dissolving the magnesium fluoride in pure water, so initially we've got 0 of these 2 ions, and in a saturated solution, the fluoride concentration is 2.4 times 10 to the negative third. Whenever you see the word saturated, you want to think equilibrium. So a saturated solution is at equilibrium. So that means that the equilibrium concentration of fluoride is 2.4 times 10 to the negative third. I can figure out what my change is, and then I know that my change row is going to match my mole ratio, so these will be in a 1:2 ratio. So this right here is going to be 1/2 of whatever this value was. So that is 1.2 times 10 to the negative third. And then I'm going to go and I'm going to plug this into my K expression and solve. So that's 1.2 times 10 to the negative third, 2.4 times 10 to the negative third, and then don't forget to square it. That's the most common mistake I see, is just forgetting to square it. So you end up with 6.9 times 10 to the negative 9th. Remember, K values are always unitless by definition. So that's A. Now let's go on to B. So B says, imagine that you have a solution that's got calcium ions and barium ions in it of the same concentration, and you're going to slowly add in some fluoride ions. You're also adding sodium ions, but I'm going to ignore them because they're a spectator. Sodium ions tend to not stick with anything. And the question is, which solid will precipitate first? Calcium fluoride or barium fluoride? And we are given the Ksp values for these two solids. Okay, I'm going to write those out. And if you take a look at those, you want to ask yourself, which solid is less soluble? Let's see, 2F minus. And if you look at these values, notice how calcium fluoride has a smaller Ksp value. And so the way that I typically think about a question like this is I look at the value of Ksp, and I'm going to say the one with the smaller Ksp value is less soluble. And if it's less soluble, that means it is easier to precipitate. So that one is going to form a solid easier. And we can actually see this mathematically. Let's take these reactions and flip them around. So if I were to reverse this reaction and say calcium ions plus fluoride ions makes calcium fluoride, this is going to look like a precipitation reaction like we did back in Unit 4, I think it was. And if you remember our rules about the value of K, when we reverse a reaction, we take the inverse of the K value. So the K value of the reverse reaction is going to be 1 over 10 to the negative 11. And if I look at my barium one, I'll write that out real quick, the K value for this reaction is going to be 1 over 1.8 times 10 to the negative 6. Notice that when you divide K by a smaller number, you end up with a larger K value, right? So the one with the smaller Ksp value, which is your calcium fluoride, is going to have a larger K value when we look at the reverse reaction, the precipitation. So it looks like your calcium and fluoride are better at precipitating. This is a more favorable reaction than your barium fluoride precipitation. So your calcium fluoride is what is going to precipitate out first because it's less soluble, it's easier to precipitate. The other way in which you can think about this is way number 1 to think about this problem. The other way to think about it is in terms of Q versus K. So if I'm going to write this out here, if you were trying to think about, at what point does this equilibrium start forming a solid, you're basically asking yourself, at what concentration will this reaction begin to shift to the left? And we know that a reaction will proceed to the left when Q is greater than K. Remember, the way you find Q is the same way in which you find K. You just plug the concentrations into this formula right here. So this is your K expression. To solve for Q, you would just plug in the given concentrations of calcium and fluoride. And if you think through this scenario, as you're gradually adding fluoride ions to your mixture, your amount of fluoride is gradually increasing. Your concentration of fluoride is increasing. So your value of Q is getting bigger and bigger as you add fluoride until eventually you reach the point where Q is now greater than K. And at that point, the reaction is going to proceed left and you will form a precipitate. So if Q is greater than K, it's going to proceed left. Write this down. And in the context of Ksp, that means you're going to form a precipitate. And when your K value is relatively small, it doesn't take much ions in order for Q to be greater than K. So that's another way of thinking about it mathematically. This is why solids with relatively small K values will precipitate easier, because it does not take very many ions to reach a point where Q is greater than K. So that's the other way of thinking about it. Okay, so going ahead to this next one, we've established that calcium fluoride is our less soluble salt. It's going to precipitate first, and it will start doing that when Q is greater than K. And so keeping that in mind, we're going to calculate the concentration of fluoride necessary to precipitate that salt. So if you think about what we know this is our Ksp expression for calcium fluoride. We know that the value of Ksp for calcium fluoride is 3.5 times 10 to the negative 11. The concentration of calcium ions in the solution is 0.1 molar. So those things we know for sure, those are fixed values. Looks like the only thing we don't know is the concentration of your fluoride ions. So we are going to rearrange and solve for F. And when you do that, you end up with your value of F being, let me check my math here real quick, ends up being 1.9 times 10 to the negative fifth, and that's a molarity. And if you think about what that number represents, that is what the concentration of fluoride ions when Q is equal to K. So any drops of fluoride that you add beyond this point, Q is now greater than K, and so you're going to form a precipitate. So this is kind of like the tipping point concentration when your precipitate starts to form. And then this B triple I, this is just an application of molarity, so it's just like applying your concentration skills. And if we write down what you know that the initial concentration of the fluoride ions is 0.2 molar. We're going to add some fluoride to our 500 ml solution, and until we reach the final concentration of 1.9 times 10 to the negative fifth molar. And then the question is, what volume is needed in order to do that? So this is, it looks like a dilution problem. It's an M1V1 equals M2V2. And your M1 is 0.2 molar. Your V1, that is your unknown. Your final molarity, it's pretty small. Your final volume is going to be 500 milliliters. And then when you stop and solve for your volume, you end up with 4.7 times 10 to the negative 2 milliliters, which is what, 0.047 milliliters. So it's a pretty small amount. You need, like, just barely a drop of fluoride ions in order to form a precipitate. And that is because your calcium fluoride is pretty insoluble, so it doesn't take very much for it to precipitate. All right, hope this helps. Let me know if you have follow-up questions.